Welcome to the deep dive. We take your requests and dive deep into whatever source material you provide.
That's right.
And today we're diving deep into the world of medical gases.
Okay.
Now, you sent in a request wanting to learn more about how these gases are stored, delivered, and used.
Yes.
I think a lot of people walk into a hospital room and they see an oxygen tank and they don't think twice.
Right.
But have you ever actually stopped to think about how those gases get to the patient's bedside?
Yeah. It's a fascinating process.
It really is. And we have with us today an expert who's going to walk us through this whole thing.
I'll do my best to break it down.
We'll be looking at a PowerPoint presentation all about medical gases.
Okay. That's good.
So let's jump right in. Now, we all breathe air, right?
That's right.
So why do we need these separate oxygen tanks in a hospital?
Well, the air we breathe is only about 21% oxygen.
Okay.
And the rest is mostly nitrogen. And so when someone is having trouble breathing, that 21% just isn't enough.
Ah, I see.
So concentrated oxygen allows their lungs to work more efficiently.
So it's like a boost.
Exactly. It gives their body the extra oxygen it needs when it can't get enough on its own.
Makes sense. Now, I know oxygen is the big one.
Right.
But it's not the only medical gas out there.
Not at all. There's also compressed air, which powers a lot of medical equipment.
Oh, okay.
And then there's carbon dioxide. It has some surprising uses, actually.
Really? Like what?
Well, for example, did you know it's used to calibrate blood gas analyzers?
Oh, wow.
Yeah, it's crucial for making sure those analyzers are giving accurate readings, which doctors rely on for all sorts of things.
That's pretty amazing. I wouldn't have guessed that.
Yeah, it's one of those things you don't really think about until you learn about it.
So oxygen, compressed air, carbon dioxide. What else is there?
Well, there's helium, which you might think of as a fun party gas.
Right. Balloons and squeaky voices.
Exactly. But medically, it can actually help people with severe airway obstructions breathe easier.
Really?
It's mixed with oxygen, of course, but the helium helps the gas flow more smoothly.
That makes sense.
It's like giving their lungs a little extra help.
Okay. Now, are there any other interesting ones?
Oh, absolutely. There's nitric oxide, which is actually a toxic gas on its own.
What?
Yeah, but in very small amounts and carefully mixed with oxygen, it's used to treat a serious lung condition called pulmonary hypertension.
Interesting. So it's like a delicate balance.
Exactly.
Yeah.
Too much is dangerous, but just the right amount can be incredibly helpful.
That's wild.
And of course, we can't forget about nitrous oxide.
Oh, yeah, laughing gas.
That's the one. It's often used as an anesthetic. But just like with nitric oxide, it's always mixed with oxygen for safety.
Right. So it's not just pure laughing gas they're giving people.
Nope. Safety first.
Okay, so we've got our lineup of medical gases here, but how do they actually get from their raw form into those pressurized tanks we see in hospitals?
So each gas has its own unique production process. Oxygen, being the most common, is usually produced through fractional distillation.
Fractional distillation. That sounds complicated.
It's actually a pretty clever process.
Yeah.
Imagine you're trying to separate a mixture of different colored candies.
Okay.
If you shook them on a slanted surface, they'd roll down at different speeds based on their size and weight, right?
Yeah.
Well, fractional distillation is kind of like that. They cool air down to super low temperatures,
Okay.
which causes all the different gases in the air to turn into liquids.
Huh.
And then, because each gas has a different boiling point, they separate out just like those candies rolling down the slope.
So they can just collect the liquid oxygen.
Exactly.
Fascinating. So fractional distillation for oxygen. What about the other gases?
Well, there's also something called an oxygen concentrator.
Okay, what's that?
It's basically like a super filter that removes nitrogen from the air, leaving behind a concentrated stream of oxygen.
So it's like concentrating the oxygen that's already in the air.
Precisely. And these are really useful for home healthcare settings.
Got it.
Now, compressed air is much simpler. It's literally just air that's been squeezed into those cylinders at high pressure.
Okay, no fancy separating required there.
Nope.
What about carbon dioxide?
To produce carbon dioxide, they heat limestone with water, which releases CO2.
Yeah.
And then they capture and purify it, and then liquefy it.
Okay.
And helium and nitrous oxide, they both come from natural gas.
Oh, interesting.
They use a process called liquefaction, which involves cooling the gas down to really low temperatures.
So they all have their own unique journeys, basically.
Exactly. But producing the gases is just the first step. We also need to make sure those cylinders they're stored in are safe and reliable.
Right, because you don't want to be messing around with pressurized gas.
No, you don't.
So let's talk about those cylinders themselves. What makes them so special?
Well, you can think of them kind of like mini pressure cookers.
Okay.
And there are strict regulations from the DOT, the Department of Transportation, about how they have to be made.
So they're not just any old metal tank.
Nope, they're usually made of steel or aluminum.
Okay.
And they have to go through all sorts of testing to make sure they can withstand the pressure.
I bet. And what about explosions? Are there safety features to prevent that?
Absolutely. There are relief valves that release pressure if it gets too high. Different types of valves and plugs, all designed to prevent explosions.
Smart. So they're designed to handle the pressure, but how do you even know how much gas is left in a tank? It's not like you can just open it up and look inside.
That's a great question, and it actually depends on whether the gas is compressed, like air or oxygen in its gaseous form, or liquefied, like carbon dioxide or nitrous oxide stored as liquid.
Oh, so there are two different approaches.
That's right. With compressed gases, the volume is directly related to the pressure.
So you can just check the pressure gauge.
Exactly. That tells you how much gas is left.
But what about the liquefied gases?
For those, the pressure stays constant until all the liquid is turned back into a gas.
So the pressure gauge wouldn't tell you how much is left?
Nope. In those cases, you actually have to weigh the cylinder.
Oh, wow. That's interesting.
It's all about the physics of how these gases behave under pressure.
Right. So, speaking of pressure, how do healthcare professionals figure out how long a cylinder will last at a certain flow rate?
It's a crucial calculation, especially when you're dealing with something like oxygen therapy.
I bet. Walk us through it.
So for compressed gas cylinders, there's something called a cylinder factor.
Cylinder factor.
It basically tells you how many liters of gas you get for each unit of pressure.
Got it. And do bigger cylinders have bigger factors?
Exactly. To calculate the duration of flow, you multiply the pressure in the cylinder by that cylinder factor.
Okay.
And then you divide that by the flow rate, which is measured in liters per minute.
So, for example, if you have a cylinder with 2,000 psig and a flow rate of 5 liters per minute.
You'd multiply 2,000 by the cylinder factor. Let's say it's 0.16 for this particular cylinder.
Okay.
So it's 320. And then divide that by the flow rate, 5, which gives you a duration of 64 minutes or a little over an hour.
Huh. That's actually pretty straightforward.
It is. Now, for liquefied gases, we use the weight of the liquid gas to determine how much gas is available.
Makes sense. So how do you do that?
We know, for example, that 1 liter of liquid oxygen weighs 2.5 pounds and produces about 860 liters of gaseous oxygen.
Okay.
So if you have a cylinder with, let's say, 5 pounds of liquid oxygen.
You'd multiply 5 by 860, which is 4,300, and then divide that by 2.5, which gives you 1,720 liters of gaseous oxygen.
You got it.
And then you just divide that amount by the flow rate to get the duration.
Exactly.
Wow. It's amazing how much math goes into something as seemingly simple as an oxygen tank.
It is. But that's just for individual cylinders. Imagine scaling this up to supply an entire hospital.
Okay, yeah, that's a whole other ballgame. So how do they manage the gas supply for a whole building?
That's where bulk supply systems come in.
Okay, tell me more about that.
Instead of relying on individual cylinders, hospitals have these central piping systems that deliver gas from a central source.
So it's like a giant network of pipes.
Precisely. And they run throughout the building, delivering gas to different areas.
That's pretty impressive.
And these systems have all sorts of safety features. Well, for example, there are main alarms that go off if there's a drop in pressure or if the flow from the source gets interrupted.
That's good. So they know right away if there's a problem.
Exactly.
Yeah.
And there are also zone valves that can shut off the supply to certain areas, like for maintenance or in case of a fire.
Oh, that's smart. So it's like a safety net for the whole hospital's gas supply.
Exactly. Now, to get the gas to individual patients, they use wall outlets that are connected to this piping system.
Okay, that makes sense.
And those outlets are placed strategically throughout the hospital.
Right.
So gas is always readily available when and where it's needed.
But how do they make sure they're connecting the right gas to the right outlet? You wouldn't want to mix up oxygen and nitrous oxide.
You're absolutely right. That's why they have these ingenious safety systems.
Okay, tell me more about those.
Well, the first one's called the American Standard Safety System, or ASS.
ASS. Okay.
And it uses threaded connections, and each gas has a unique thread size and type for both the cylinder and the outlet.
So you literally can't connect the wrong gas.
It would be like trying to fit a square peg in a round hole. It just won't work.
That's reassuring. What about the other systems?
So there's also the Pin Index Safety System, or PISS, which is used for smaller cylinders.
PISS.
And it uses 2 pins that have to align with corresponding holes in the valve.
Kind of like a key.
Exactly.
Yep.
Each gas has a specific pin position, so you can't accidentally connect the wrong one.
That's so clever.
And lastly, there's the diameter index safety system, or DIS.
Oh, DIS. Okay.
This one uses color-coded and index connectors, so you can visually see if you're trying to connect the wrong gas.
So they've got multiple layers of protection built in.
Yep. Safety is paramount when you're dealing with medical gases.
Makes sense. So we've talked about the cylinders, the piping systems, and the safety features. Is there anything else we need to know about how these gases are delivered?
Yes, actually. There's one more crucial component: regulators.
Okay, tell me about regulators. What do they do?
Regulators are basically pressure valves. They take the high pressure from the cylinder or the central piping system,
Right.
and they reduce it to a safe, manageable level for delivering to the patient.
So they're like the gatekeepers, making sure the gas flow is controlled and safe.
That's a great way to put it. And there are different types of regulators for different applications.
Oh, really?
Some have preset pressures,
Okay.
while others allow healthcare professionals to adjust the pressure as needed.
Wow. This is also fascinating. We've learned about the different types of medical gases, how they're produced, the safety features, and the bulk supply systems.
I covered a lot.
It's amazing how much thought and engineering goes into something as seemingly simple as delivering oxygen to a patient.
Right. It's a hidden world that most people don't even know exists.
Exactly. And we've only just scratched the surface. There's a whole other world to explore when it comes to the devices that actually measure and control the flow of these gases.
Yes. Flow meters.
That sounds like a whole other level of precision. I'm definitely intrigued.
It is. And we'll dive into that after a quick break.
Sounds good. Stay with us.
We'll be right back. Welcome back. So before the break, we were talking about regulators.
Right, those pressure valves that control the gas flow.
Exactly. Now let's talk about flow meters.
Flow meters. Okay, what are those exactly?
They're the devices that actually measure the flow rate of the gas.
Ah, so they tell you how much gas is being delivered per minute?
Precisely.
Yeah.
Usually in liters per minute. And they come in a few different types.
Oh, interesting. Like what?
One of the simplest is the flow restrictor.
Flow restrictor.
It's basically a fixed orifice that allows only a specific flow rate.
So it's like a preset flow rate.
You got it. And they're often used for low flow applications, like with nasal cannulas.
Makes sense. So flow restrictors for when you need a fixed rate. What about when you need more control over the flow?
Then you would use an adjustable flow meter. A common one is the Borden gauge flow meter.
Borden gauge.
It has this curved tube that straightens out as pressure increases.
Huh.
And that movement is translated into a flow rate reading on a dial.
So like a speedometer for gas.
Exactly. The more pressure, the higher the flow rate.
Cool. So Borden gauges are pretty common then.
They are. They're simple, durable, and relatively inexpensive.
Makes sense. Are there any other types?
Yeah, there's also the Thorpe tube flow meter.
Thorpe tube. Okay. What's that one like?
It's a vertical tube with a little float inside.
Okay.
And as gas flows through the tube, it pushes the float upward.
So the higher the flow rate, the higher the float goes.
Exactly. And there's a scale next to the tube that shows you the flow rate based on the float's position.
So it's a visual indicator of the flow rate.
You got it.
Now, I'm guessing there are different kinds of Thorpe tubes too.
You're right. There are compensated and uncompensated Thorpe tubes.
Oh, okay. What's the difference?
It all comes down to back pressure.
Back pressure. Now, what's that?
It's any resistance to the gas flow downstream from the flow meter. Like if there's a kink in the tubing.
Ah, I see. So it's like a blockage.
Exactly. And uncompensated Thorpe tubes are affected by that back pressure, so the readings can be off.
But the compensated ones are designed to handle it.
Exactly. They minimize the effects of back pressure, so you get a more accurate reading.
So if you need a really precise measurement, you'd want a compensated Thorpe tube.
That's right.
This is all fascinating stuff, but let's zoom out a bit. We've talked about the production, storage, and delivery of medical gases, but what are some of the challenges that come with managing this whole complex system?
Well, one of the biggest challenges is ensuring a constant, uninterrupted supply.
Yeah, I imagine that's crucial in a hospital setting.
Absolutely. Any disruption in the supply chain could have serious consequences.
It's literally life-saving stuff we're talking about here.
Exactly. Another challenge is managing costs. Medical gases aren't cheap.
Right.
And hospitals have to balance the need for a reliable supply with their budget.
Makes sense. And I imagine safety is a big concern, too.
Well, absolutely. We talked about all the safety systems in place, but human error is always a possibility.
You can't eliminate that completely.
Nope. So proper training and following protocols are absolutely essential to prevent accidents.
Right. Now, I'm also wondering about the environmental impact.
Good point.
Some of these gases, like nitrous oxide, are greenhouse gases.
That's right.
So Are hospitals doing anything to be more environmentally friendly?
Yes, definitely. A lot of hospitals are implementing programs to reduce their emissions.
Like what?
Things like capturing waste anesthetic gases, using more efficient delivery systems, and exploring alternative gases with a lower environmental impact.
So they're making an effort to be more sustainable.
Absolutely. It's becoming increasingly important.
It's really impressive to see how much thought goes into managing this complex system. It's like a whole hidden world behind the scenes of healthcare.
It truly is. And it takes a lot of dedicated people working behind the scenes to make sure it all runs smoothly.
Speaking of dedicated people, I have to say you've been amazing at explaining all of this.
Well, thanks. I'm glad you're finding it interesting.
I am, definitely. And I think our listeners are too.
I hope so.
Before we wrap up, I want to emphasize one key takeaway here.
Okay.
Medical gases are more than just commodities.
Right.
They're life-saving therapies.
Exactly.
And their proper handling and administration are absolutely crucial.
Couldn't agree more.
We've seen how everything from cylinder design to safety systems is carefully engineered to ensure patient safety.
Right.
And those flow emitters and regulators we talked about, they play a vital role in making sure patients receive the right dose of gas at the right time.
It was all connected.
It really is. It's amazing how much science and engineering goes into something we often take for granted.
It's a fascinating field, and it's always evolving.
Well, we've covered a lot of ground today, but as with any deep dive, there's always more to explore.
Oh, absolutely.
I encourage our listeners to stay curious and keep asking questions. And I have a feeling this won't be our last deep dive into the world of medical gases.
I agree. There's always something new to learn.
Well, on that note, we're going to wrap up this episode of The Deep Dive. Thanks for joining us on this journey of discovery.
It's been my pleasure.
Until next time, stay curious.
Welcome back to The Deep Dive. We've spent this episode exploring the world of medical gases.
We've learned about how they're made,
how they're stored,
how they're delivered,
and all the intricate systems that ensure they're used safely and effectively in hospitals.
It's pretty amazing when you think about it.
It really is. It's like a whole hidden world operating behind the scenes of healthcare, making sure those life-saving gases are always available.
And it all starts with those seemingly simple oxygen tanks.
But as we've seen, those tanks are just the tip of the iceberg. There's so much more to it.
A lot more than meets the eye.
Exactly. So as we wrap up our deep dive today, I want to leave our listeners with one final thought.
Okay.
We've focused mainly on how these gases are used in hospitals, but their applications go way beyond that.
Oh, absolutely.
Think about scuba diving, for instance.
Right. Divers rely on compressed air and sometimes other gas mixtures to breathe underwater. Exactly. And then there's the aerospace industry, where gases like oxygen and nitrogen are essential for rocket propulsion and life support systems.
You know, it's incredible how these gases are used in so many different ways.
It really is, and we often don't even realize it. So the next time you see an oxygen tank or hear about some new use for medical gases, I hope you'll think back to this deep dive and appreciate all the complexity and importance behind it.
And remember, there's always more to learn.
Always. Keep those minds curious, keep asking questions, and never stop exploring the world around you.
Couldn't have said it better myself.
Thanks for joining us on this journey of discovery. This has been The Deep Dive. Until next time, stay curious.